In this video, we consider our first NP-complete problem, and we show that this problem is NP-complete. And the problem we are looking at is the so-called satisfiability problem set. And we'll show that set is NP-complete. This is actually also called Cook's theorem, or the Cook-Levin theorem. First question is, of course, what is set? Set is the so-called satisfiability problem for propositional logic. And the problem is, given a formula in propositional logic, is the formula satisfiable? Satisfiable. That's the satisfiability problem. Okay, let's take an example. This might be a formula in propositional logic. We have propositions, atomic propositions like A, B, and C. And we use these propositions to build a formula like this one, A and not B or C. Question is this satisfiable, yes or no? And what we can do is we just guess some valuations of the A's and B's. For example, if we set this one here to 1, so to true, then the formula is true anyway, so we can more or less set whatever we like for the other atomic propositions, and we obtain a valuation of the atomic propositions that makes this formula true. So this formula here is satisfiable. So this is satisfiable, apparently. Consider another formula like this one, A and A implies not B, and B, for example. If we have this formula is not satisfiable. You can try, you can check all the possible combinations. You won't be able to find a satisfying valuation of the A's and B's. So this is not satisfiable. Satisfiable. Why? Because we have to make A true, so this needs to be 1. If A is 1, then we have this implication here. If A is true, this means that not B must be true. If not B is true, then B must be false. But this last conjunct B here requires B to be true, so we have a problem here. And this formula is not satisfiable. So that's actually the problem. And the first part of the proof is to prove that the satisfiability problem is actually an NP. That's the first part, and that's quite easy. Set is in NP. So we need a non-deterministic algorithm to determine whether a formula is satisfiable or not. And the non-deterministic algorithms usually proceed just by guessing an answer. And the thing we are guessing here is the valuation of the atomic propositions. So the first step is we simply guess a valuation of the atomic propositions, more or less like we did here. We simply guessed something. And second step is check. Check if formula evaluates to true for this valuation. That's what we did in the second step here. The evaluation can be done, of course, in polynomial time, because we just have to scan the formula from the innermost to the outermost parts and check what the result is. So this can be done in polynomial time, and we can conclude that the satisfiability problem is actually an NP. So we have so far seen that the satisfiability problem is in NP, and the second part of the proof, that's actually much more complicated, is to show that SAT is NP hard. So we have to show that the satisfiability problem SAT is NP hard. NP hard. This proof might seem tedious and long, and it is unfortunately very long. However, it's interesting nevertheless, because it shows how to encode a Turing machine into a logical formula. So what we will be doing is encoding a Turing machine in propositional logic. Propositional logic. This might seem quite technical. However, it has practical applications because there are tools around that have heuristics implemented to solve propositional logic. And in this video, you get an idea how to encode some problem into propositional logic. And this idea might help you in other cases. So actually, even if you're not that interested in this specific encoding, you might want to see the general idea how to actually encode arbitrary problems into propositional logic, what techniques to use. So even if you're not really interested in the technical details, it might be worthwhile watching the video anyway. So how does it work? We have to show that it is NP hard, and to show that the satisfiability problem is NP hard, we have to show that every problem that is in NP is polynomial time reducible to our satisfiability problem. And to start with, we'll simply take one problem. We'll take a problem, and that's called A. So we take one problem from NP. So this problem is in NP. If this problem is in NP, then there must be a polynomial time non-deterministic Turing machine. So then there is a non-deterministic TM for exactly this problem, M for A, which decides and the question is, given an x with the letters x1 to xn, and it checks whether this input is actually in A. And it decides in polynomial time, and we'll fix this polynomial time in time p of n. And this p of n has a polynomial bound, nomial upper bound. So that's what we know so far. So if we take a problem that's an NP, there must be a Turing machine that actually decides it. So how does it work? So we have a Turing machine. What do we know about the Turing machine? This Turing machine has some states. And it has a tape. And on the tape, we have the input, x1, x2, so on, to xn. So that's the input. Initially, we know that the Turing machine is in this state here. So we know that initially, we start here. We further know that initially, the head is here. That's also what we know. So, initial state, this is the input is on the tape. Input on tape. This is the Turing machine M. Turing machine M. Now, the Turing machine starts. And what it does is it changes state. And at some point, this, we assume that this word is actually accepted, and at some point the Turing machine will accept the word. So we have some steps, and we know how many steps we have, and this is actually P of n steps. So after P of n steps, we have the following situation. We have still the Turing machine with the control. This should be the final state with the control. And now we are actually in the accepting state. So we are here. After P of n steps. Now, what happened on the tape? We don't know what's really on the tape, but we know something. There's something on the tape. And the head is somewhere. Something we don't know. But there's one thing we know, and we know how far we can we could have gone, how far we might have gone. To move the head one step to the right or one step to the left, it takes one computational step. So if we have P of n steps in total, this means that the only cells that are reachable to the left are at most P of n steps to the left and at most P of n steps to the right. It's impossible to visit or to scan more cells on the tape because we only have P of n steps for the computation of the Turing machine. After this P of n steps, the Turing machine halts. So we need that. We know that we can only reach P of n cells to the right and to the left. So more is impossible because each tape movement requires one step. One step. So that's our situation so far. We know that we have this language A, we have a Turing machine. When the Turing machine accepts a word, it works more or less like this. And the idea for the proof now is that we want to construct a formula that actually encodes the behavior of the Turing machine. So the idea is for an input W, we construct a formula FW. And this formula Fw should be satisfiable such that A accepts W, so W is an A, if and only if Fw is satisfiable. And there's one important part. And this construction here must be done in polynomial time. So the idea is actually to construct a Turing machine that mimics the behavior of the Turing machine for this specific input W. There are parts that are fixed. The Turing machine itself, Tm is fixed. So the Tm M is fixed. The thing that varies is the input X. Okay. For this encoding, we need to encode three different things. If you look at our Turing machine here, we need to encode. First thing is, what's the current state? Second thing we need to encode is where's our head? And third thing is what's on the tape. So what we will do is we encode first the state. So first thing is encodes the state. And to encode the state, we'll use a propositional variable. And the propositional variable will be called st for state, t with index t and q. So we'll get a lot of variables just for encoding the state. And t actually varies from 0 to p of n, and this encodes the time. And q is simply a state of the Turing machine. And the idea is that st with the index tq equals 1 if the Turing machine is in state q after t steps. So for every step in time, for every moment in time, we get a variable st, and for every state as well. And the idea is that as we have only Boolean variables, we set it to true if the Turing machine is in this state after t steps. Then this variable should be true. That's the idea. And using this idea, we can encode the current state. Now we have encoded the state. Second part we have to encode is the position of the head. So encode position of the head. And we use a similar idea to encode the position of the head. We'll use a propositional variable, which can be true or false again, and this propositional variable will be called pos for position. And here the position depends again on the time t and on the position I. And t will vary from 0 to p of n, again because it models the time. And this Turing machine only has p of n steps, so these are the only time stamps we can actually have. And the I is the position of the head. And we have already deduced that the head can only move from minus p of n to plus p of n. So I is something from minus p of n to plus p of n. And this is the position of the head. And here the idea is that pos, the variable for t and I, is true if and only if the Turing machine, Tm, the head, Tm head, is at position I after t steps. But unfortunately we are not done yet, so I had to erase this part. So the state was encoded with these variables st with the index t and q, and the position was encoded with this variable pos with the index t and I. But there's one thing more we need to encode, and that's actually the contents of the tape. So we still need to encode the tape. That's the third part. So encode tape contents. And to encode the tape contents, we again will use a propositional variable, which we'll call tape. This has three indices. First one is the time t. Next one is the position, where it's on the tape. So it's the time, where it is on the tape. And third one is what is actually on the tape, so the a. Again, the t is something between 0 to p of n, still the time. the I is the position, so it's from minus P of n to plus P of n. It's a position. And third one is the A, and the A is something from the tape alphabet. This is the gamma, the uppercase gamma, so A is the letter that's on the tape at this point in time, at this position on the tape. And the idea is, this is the tape alphabet, tape content. And again, the idea is that this propositional variable tape, the index t, I, and a, is equal to 1 if and only if the tape cell, at position I contains the letter A after t steps. So now we have fixed the variables that we'll use in our formula, and now we have to encode the actual behavior of the Turing machine in the next step. And now we have to encode the behavior of the Turing machine, so we start with the encoding. The first problem we have, as we have introduced these propositional variables, for example for the state, is now we have to ensure that that for each point in time there's only one propositional variable that's actually true, and not more than one. Because otherwise we might find a solution that would specify that the Turing machine is in 2 states or 3 states at once. And that's of course impossible, so we have to encode the constraint that the Turing machine is for each position in time only in 1 state. And similarly, that the head is only at 1 position, and it cannot be at multiple positions. So we have to encode all these constraints in logic. So what we'll do is we'll construct a formula C for the constraints that we put on these variables. So it's only the first part of our formula. And what we would like to ensure is that for all points in time, so for all points in time t, here t is a variable that starts from 0 and goes up to p of n. This one here is a generalized end, so this is actually an end. And this yields a large conjunction. So this is an end, so means for all points in time. We have to ensure that the Turing machine is only in 1 state. So it must be in 1 state, so one of these state variables must be true. So to ensure that one must be true, we have a disjunction. This is a generalized OR. So this here is an AND. This one here is an OR. And for all the points in time, it must be in 1 state. So there must be one index I, which starts at 0 and goes up to the number of states that we actually have. And one variable must be true, so state must be true for this point in time, and this state qi. So there must be at least one state in which the Turing machine is in. One must be true. On the other hand, we have to ensure that there is only one and not more, that the Turing machine is not in more than 1 state. And to ensure that it is not in more than 1 state, we use a second formula, and this says, okay, we take all the states, now I use the index j, and again I start with 0 and go up to the number of states. It's -1 by the way. No, -2, sorry. And take another state, L, which is some different state. Here we start at j plus 1, and I go to number of states q minus 1. And what I would like to specify is that it is impossible that two state variables are true at the same time. So I would not allow that for this fixed point in time, st is true for this point and the state q j and state q l. So this part here reads for all points in time. This means Tm must be in at least one state, because one of these variables needs to be true at point t. And this one here means that it is there's at most one state for which it is true. It's impossible to have for the same point in time t two different states that the Turing machine is in. So this means Turing machine cannot be in two states at once. Tm cannot be in two states at once. We always go to the index. The indices I usually go from 0 for the states, from 0 to the amount of states in -1. -1 is because we start our numbering with 0. As we start our numbering with 0, it just goes to number of states -1. Same here, we just go to number of states -1. And here, as we consider only need to consider every pair only once, we can start the second conjunction after the first, so that we don't get duplicate pairs. Makes the formula a bit smaller. That's why we start here with j plus 1. Okay, so this is the part for the states. Turing machine can only be in one state at a given point in time. We have to do the same for the position. So we'll add for the position the same things. So for the position we have to add the Turing machine is in one position. So we'll add, I put parentheses around, we'll add for each position. The position starts from minus p of n and goes to p of n. And we know that the position was encoded with the variable pos. So the Turing machine, the head of the Turing machine is at one position, and it is at most at one position. So we know and now same construction here. We start with j from minus p of n to p of n minus 1, and we have an L that starts at j plus 1 and goes to p of n. And it is impossible to have the head at two positions for the same time, so for the time t and j. Only one can be true, so either this or this must be false, so t or l. So this one here encodes the same requirement for the position of the head. head is oh, sorry, at one position, this is not at two positions. Okay, now we have encoded the positions, and now we do the same thing for the tape contents. There can be only one letter on the tape, so we have to add even more formulas. So we have to add again that for all i's from minus pi of n to plus pi of n. So for all positions, these are the positions on the tape. We know that one letter must be there, so we go from here we start. Let's say we start our, counting with 1. Well, we can only start at 0. There must be one letter on the tape, so tape T I A K must be true. And there's only one, so again we have all the others. They're not more than one. So from k equals 0 to, this is the size of the alphabet, minus 2, and L starts with k plus 1. Ah, no, it's not k, sorry. This must be, of course, a j. This one is a j, and it goes to gamma minus 1. And again, it's not possible that there are two symbols on the tape, so tape point in time t, position I, this is aj, the j's symbol, and tape t I a l, and they cannot be true at the same time. So this is actually the formula, and I'll go through it in detail. This one here is, again, it's for all tape positions. This is one of the letters is in the cell. This one here is only one. Not two. Say not two letters are in the same cell. Same cell. After t steps, and the position of the cell is given by I. So these three the index t is the point in time, the index I is the position on the tape, and aj and al are the contents of the tape, and only one of these can be true. It's impossible to have two that are true at the same time. So this is actually a huge formula, just encoding that we have only one state, only one position, and only one contents on the tape. So here the idea is only one state, only one state, only one only one, sorry, only one position, and this is only one content. One important part to consider at this point is how big is this formula actually. This one here we have a conjunction for all the points in time. The points in time go from 0 to p of n. So this one here, this has an upper bound, so it's somehow in the class of p of n. This is the big O notation, so meaning this is a constant, it's up to a constant factor, a multiple of p of n. So this goes from 0 to p of n. This one here is constant. This is constant because it's fixed. It's just the number of states of the Turing machine, so it's a fixed value. So this is fixed, and this is also fixed. Fixed or const. Okay, this one here. This disjunction is also from minus pi of n to plus pi of n, so it's 2 times p of n. So it's also in O of p of n. This one here, that's the more complicated part. This one here is a double conjunction, and this double conjunction, this one goes from p of n, from minus p of n to plus p of n more or less, and this one as well. So this is actually in O of p of n square. And this one here is constant again, constant. And this is constant. Because the tape alphabet is something that's constant, that's independent of the input. This one here is again in O of p of n. Okay, now we have to summarize. This AND operator goes from 0 to p of n. This one here is something constant. This is something in p of n, but this is in p of n square, and it's inside this one here. So actually we have, this is the important part, we have 3 nested conjunctions. Each of these conjunctions goes from more or less 0 to p of n, or multiple of it. So as we have 3 nested conjunctions here, this one, this one, this one, actually the whole formula is in O of p of n to the power of 3. Because of these 3 nested conjunctions. Each of these conjunctions being in the range of p of n. All the others, they're not that important because they have a lower exponent. Many of these are constant. So this is actually the first part of the encoding. Now we start with the encoding of the initial configuration. Initial configuration means the point in time is 0. And the formula for the initial configuration is, the first one is, we have to encode that we start at an initial state. So the Turing machine should be in an initial state when it starts. So the formula S, which is defined by the proposition ST0, because it's time 0, and Q0, meaning that the Turing machine starts at Q0. Then the position of the head, where is the position of the head initially, so index 0, and initially the head is at position 1 on the first letter. Now we have to encode what's on the tape. So on the tape is of course the input word, which was this input word x, from x1 to xn. So we start with j equals 1, go up to n. And now we have on the tape for time index 0, position j, and the letter we have is x j. So that's actually what's on the tape when we start the Turing machine. However, we have to encode what is in all the parts of the tape that's not part of the input. And that's a blank. And this has to be encoded as well. So we have to encode the blanks. And the blanks are encoded by a first conjunction j that starts at minus p of n, goes up to 0. Again, that's the tape position. And here on the tape, for time index 0, position j, and the element we have here is the blank. And similarly, these are the blanks to the left. Similarly, we have the blanks to the right. The blanks to the right, they start after the input. So at position, the input goes up to position n. So here we start at position n plus 1 and go up to p of n. And again, we have only blanks. So the variable tape time index 0, position j, and blank must be true. And this is actually the encoding of the initial configuration. This means initial state is Q0. This one here is initial position is 1 for the head. Here we have x1 up to xn is on the tape in the cells from 1 to n. Here we have blanks to the left, blanks to the left, and here we have blanks to the right. So that's actually all we need to specify for the initial location. This one here always is the time index. Time index, this one here as well. So you see they're all zeros because it's meant to encode the initial configuration. Now let's have a look at the size of the formula. Size of the formula. Okay, this is constant, this is constant. This one here depends, of course, on the length of the input. So it's in O of P of n. And this one as well. So the size of the formula is actually in O of P of n. So it somehow depends on the length of the input. Of course, length on the input. And this one is given, the amount of steps is given by P of n, which is the time complexity of this Turing machine. So this was the formula for the initial configuration. Next step is the encoding of the transitions. Encoding transitions. And for this encoding, I will assume that movement to the left will mean -1, no movement will mean 0, and movement to the right will be +1. Because then it's easy to write the formula. And the formula we'll get, I'll call T for transitions. And this one encodes the behavior of the Turing machine. And we consider all the points in time, T, all the possible states, Q, all the possible positions on the tape, I, and all the possible letters, A, that could be on the tape. And now we say, okay, if we are at our point in time T in a state Q, This means that if state at point in time t is q, so this variable is true, and the position, our head, at point t in time, same time, is I. So if we're at a point in time t in state q and the head is at position I, then of course we need to read what's on the tape. So we'll fix what's on the tape. And on the tape we have a letter. So the tape at this position in time, this is the position on the tape, I, and the letter we have is an A. So if we have this, so state, position, and the tape contents for this very same position. I'll mark this one here. So this is the time. The time is always the same. Sorry, this one. And this is the tape position. This is the current state. Is Q. And this means the current symbol is A. Okay, now we have fixed that the current state is Q, the current symbol we read is an A, and now we have to specify what the Turing machine does, and that's actually specified by the Turing machine itself, by the transition relation of the Turing machine. So we have to check the transition relation of the Turing machine, and this transition relation specifies what can happen. And actually the Turing machine can choose one of the possible transitions for the current state and the current symbol. The Turing machine is non-deterministic, so there might be multiple alternatives. So we have to check the alternatives, and the alternatives it can choose one, so it's a disjunction. It's a Q prime, A prime, Y prime, and how is this determined? We check the delta, the transition relation, or the transition function of the Turing machine, and check what happens if we are in state Q, which we have specified here, that we are in state Q, and read an A, which we have specified here. Then there must be some successor state Q prime that the Turing machine can choose. It can write an A prime on the tape and move the head to the left, to the right, or not at all, which will encode by Y prime. And there might be multiple possibilities, and for all the multiple possibilities we have a disjunction. And now we specify that the successor state is, of course, Q prime. So at the position in time t plus 1, the state must be Q prime. So we know that the state at time t plus 1, so in the next step, the Turing machine must be in the state Q prime, which is the chosen successor state for this possibility. And the head is moved, so we go to the left, to the right, or not at all. However, the position at point in time t plus 1, so the next step, is the old position I, and it depends whether we go to the left or to the right, so it is I plus Y prime. And here actually you see why it was convenient to encode left by -1, because if left is -1, we go 1 to the left, and right is +1, so we add 1, and if we are neutral, then we don't change I at all. So this is the successor position of the configuration. And now we have to encode how the tape is changed. And the tape is changed because we replace the letter A by A prime. So on the tape, for position t plus 1 in time, so after t plus 1 steps in time, the element at the position I, so it's the same as here, But now we don't have an A here, but we have an A prime, because the Turing machine replaced the A by A prime in this transition. So this is actually the encoding. Here is this one here selects one possible successor state. Turing machine is non-deterministic. This one here, t plus 1 is the next step. This one here is the successor state. Is q prime. This one is the new position. And this is A is replaced by A prime. So with this formula, we encoded the transition of the Turing machine, what it actually does to the tape and to the current state. And again, we have to look at the size of the formula. So the things that are important are not this one here, because this is constant anyway. It depends only on the number of states of the Turing machine. So that's only some constant. That depends on the Turing machine. However, we have to look at this one here, because here in this conjunction, this generalized conjunctions, we go through for all the possible values of the variables. This one here is our point in time. This point in time goes from 0 to p of n. This one here, it's a nested conjunction, so we consider all the pairs. So this one here is a state. This depends somehow on the number of states, which is q, but this one is constant, so it doesn't matter. This one here is the position on the tape. This was time. This is tape position. The tape position goes from minus p of n to plus p of n. This is the tape position. So this one depends on the input. It's not constant. And this one here, it's the depends on the size of the tape alphabet, which is the size of gamma. It's the tape symbol. And this one is constant again, because it only depends on the Turing machine. So the two non-constant parts are this one and this one. This one is in the order of p of n, and this one as well. So as they are nested, the size of the formula, consider all the possible pairs. So size of the formula is in O of p of n square, because this one and this one, because of these two. So this subformula is in this order. So far we have specified what is changed during a transition, but like in for the first formula, we have to specify what is not changed. So we have to specify that the rest is unchanged. Rest of the tape is unchanged. Unchanged. And I will call this formula T2, because the second part of the transition specification. So what we consider is all the points in time t, all the positions on the tape I, and all the possible symbols that might be there. And we consider all the positions on which there is no head. So all the positions on which the head is not at this point. So if the head is not at some position, so at the point in time t, the head is not at position I, and we have on the tape at this position in time t, and on the position I, we have the letter A on the tape. Then we would like to have the same letter in the next state. So then tape, the next step, so at position in time t plus 1, in the same position I, we still have the letter A. And this specifies that the tape for all the other positions is unchanged. So this is head is not on position I. Here we know we're on position I. In this cell we have an A, and here we still have an A. An A. This is time index t, time t, and this is time t plus 1. So this is what we have specified now in this formula. We again have to check the size of the formula. This one here, t is again for all the points in time. So this goes from 0 to p of n. This one here goes over all the positions on the tape, so from minus p of n to plus p of n. And this one here relates only to the size of the tape alphabet, so this one is constant. And again, as we consider all the pairs, we have the size of the formula, size of this subformula. Formula is in the range of, in the order of p of n square. Because of this, taking all the possible combinations. Okay, and finally, we have to specify that the Turing machine actually accepts a word or not. So we have to specify accepting. Accepting. And accepting is specified by a formula, which I'll call A for accepting. And in the end, we must be in some kind of final state. So there must be state Q and F such that finally, so at P of n, we must be in a final state. And that's simply a disjunction. This means there must be a final state, and in the end we are in the final state. So this one here is at the end, which is at time index P of n. We are in a final state. Now let's check the size of this formula. The size of this formula actually only depends on the amount of final states the Turing machine has. This amount is constant, just depends on the Turing machine. It's nothing to do with the input. So this one here is size of the formula. This subformula, size of formula. Formula is constant, so it's in the order of 1. It's O of 1. Okay, now we have all the subformulas, and the formula that corresponds to the encoding of the behavior of the Turing machine for a given word is FW, and now we can combine all these parts we have defined so far to formula FW. So combine the subformulas. What we get is FW, and we simply take all the parts we have. The one with the constraints, then the initial condition, the transition relation, and the second part of the transition relation, and the acceptance formula. And we just make a conjunction out of it. And after we have constructed this FW has the property that Fw is satisfiable. If and only if W is in A, because it simply mimics the behavior of the Turing machine. So if the formula is satisfiable, we know there's a satisfying valuation of all these atomic propositions we have, and from this satisfying valuation we can easily derive all the configurations of the Turing machine. And we can deduce from the last one that this one must actually be accepting. On the other hand, if there is an accepting, if the word is in the language, then there's an accepting run. This accepting run we can use to construct a satisfying valuation. So we know that this condition here holds. And we also know that the size of the formula, of this formula here, size of this formula is in the order of, P of n would be illegible otherwise, so it's P of n to the power of 3. Because we had one subformula that was actually in the order of, that has the P of n to the power of 3, and that was the constraint formula, the first one. And that's the most important one. All the other ones were less. So in the end, we have this size of the formula. And now we have to consider whether this transformation can actually be done in polynomial time. And the construction of the formula, construction of this Fw, is just writing the formula. There's nothing more complicated involved. However, the writing of the formula depends on the size of the formula. The size of the formula is in O of P of n to the power of 3. So this is in the order of P of n to the power of 3. However, if P of n is polynomial or is bound by a polynomial, then this one here is still a polynomial. If P of n is a polynomial, which was the initial assumption that the problem A is actually an NP, so there must be a Turing machine that accepts the word in polynomial time. So P of n must be a polynomial, or bound by a polynomial, Then we know, then the reduction is also bound by a polynomial. Then the reduction is in O of P of n to the power of 3, and still a polynomial. Or bound by 1. So what we have shown is that all the problems in NP can actually be reduced to our satisfiability problem. So this concludes the proof, and this means that the problem SAT is NP hard. And therefore it's NP complete.